So in the previous lesson, we got to understand that the directional derivative of a function of two variables x and y can be expressed as du f of xy is equal to fx of xy times a plus fy of xy times b, where fx and then fy are the partial derivatives of the function with respect to x and y respectively, and then a and b are the x and y components of the unit vector u cap. Now this directional derivative can as well be expressed as the dot product of two vectors. So we can have the first vector having components fx of xy, comma, fy of xy, and then the second vector having components ab. So literally, we can say that the directional derivative can be expressed as the dot product of two vectors. Now we have the first vector to be what we call the gradient of the function, and then the second vector, as usual, that is the unit vector u cap. Now in this lesson, we are going to focus more on the gradient of the function. So given that f is a function of two variables, the gradient of the function is simply a vector function, and it is given by the vector which has components fx of xy, comma, fy of xy. So notice that the gradient of a function is a vector function, and this can as well be expressed as the partial derivative of the function with respect to xi plus the partial derivative of the function with respect to yj. So basically, this is how to express the gradient of a given function. So let's take a quick example. So given that f of xy is equal to sine x plus e to the power xy, we are going to find the gradient of the function at the point 0, 1. We are going to find the gradient of the function at the point 0, 1. So let's try this together. So we know that the gradient of a function of two variables xy is given by the vector which has components fx of xy, comma, fy of xy. So basically, we need to find the partial derivatives of the function with respect to x and then y. So for fx, basically we are going to differentiate this function with respect to x, and then we keep y as constant. So first we differentiate sine x, and then we have cos x plus, we are going to differentiate e to the power xy. So we focus on the exponent. We differentiate x, we have 1, then 1 times y is y, so we are going to drop down the exponent, which is y, and then we multiply that by what we have here, so times e to the power xy. So that is for fx. And then for fy, we are going to differentiate this function with respect to y. X becomes a constant, so we differentiate this constant, we have 0 plus, focusing on the exponent, we differentiate y with respect to y, and then we have 1 times x is x, and then times e to the power xy. So we can simply say that fy is equal to x times e to the power xy. Therefore, the gradient of the function is equal to, we have fx to be cos x plus y e to the power xy, and then fy to be x e to the power xy. Now the next thing we are going to do is to find the gradient of the function at the point 0, 1. So to do so, we are basically going to substitute 0 for x and then 1 for y. So we have x to be 0, y to be 1. Therefore, we have the gradient of the function at the point 0, 1 to be equal to, we have cos 0, that is for x, and then plus 1 times e to the power x is 0 times 1, comma, x is 0 times e to the power 0 times 1. So this becomes, now cos 0 is 1, so we have 1 plus, now e to the power 0 is 1, 1 times 1 is 1, so that is 1 plus 1, comma, we have 0 times this value here, so 0 times this value is 0, so 1 plus 1 is 2, and then we have 0 here. Therefore, the gradient of the function at the point 0, 1 is equal to the vector which has components 2, 0, or better still, we can say that this is equal to 2i if you want to represent in this form. So let's move on as we take some more examples. So to example 2, we are going to find the directional derivative of the function at the point 2, 1 in the direction of the vector v, which has components negative 2, 1. Now at this point, we know that the directional derivative of a function f of xy is giving us the dot product of the gradient of the function and the unit vector u cap. So first, let's try to find the gradient of the function. So the gradient of the function is given by the vector which has components fx of xy, comma, fy of xy. So we are going to find fx and then fy, which happens to be the partial derivative of the function with respect to x and then y. So we have fx to be equal to, now considering the function f of xy to be equal to ln of x square plus y square. Now assuming that you have d dx of ln of x, you are going to differentiate x with respect to x. You have 1 divided by, you are going to repeat x. So basically, to find the partial derivative of the function with respect to x, we are going to differentiate the expression inside here with respect to x. So we differentiate x squared, we have 2x, and then we differentiate y squared, that goes to 0. So divided by x squared plus y squared. And then for fy, we differentiate this with respect to y. This goes to 0. Here we are going to have 2y and then divided by x squared plus y squared. So that is fx and then fy. Therefore, we have the gradient of the function to be equal to 2x over x squared plus y squared, comma, 2y divided by x squared plus y squared. Now the next thing we are going to do is to find the gradient of the function at the given point, that is 2, 1. So here we are going to have x equals 2, y equals 1. So that's going to be, we are going to have 2 times 2 divided by 2 square plus 1 square, comma, here we have 2 times 1 divided by 2 square plus 1 square. And that's going to be, at the numerator here, we are going to have 4. 2 times 2 is 4. And then 2 square is 4. 1 square is 1. So 4 plus 1 is 5. So we have 4 over 5, comma, here we have 2 over 5. Therefore, the gradient of the function at the point 2, 1 is equal to the vector that has components 4 over 5, 2 over 5. Now the next thing is we are going to find the unit vector. So we know that the unit vector, first of all, we are going to denote the unit vector as u cap, and that is equal to a comma b. So we have the unit vector to be equal to the direction vector divided by its magnitude. So that is equal to, we have -1, 2 divided by the square root of -1 square plus 2 square. So that's going to be -1, 2 over -1 square is 1 plus 2 square is 4. So 1 plus 4, that is 5. So we have this divided by the square root of 5. So finally we have u cap to be equal to -1 over square root of 5, comma 2 over square root of 5. Now the next thing we are going to do, that is to find the directional derivative of the function at the point 2, 1. That is the dot product of the gradient of the function at the point 2, 1, and that's 4 over 5, comma 2 over 5, and that of the unit vector. So -1 over root 5, comma 2 over root 5. So here we are going to multiply corresponding components and then we add them up. So we have 4 over 5 times -1 over root 5. So 4 times -1, that is -4, divided by 5 times root 5, we have 5 root 5, plus 2 times 2 is 4, 5 times root 5 is 5 root 5. Now you realize that here we have a common denominator, so we basically add the numerator. So -4 plus 4 is 0, so we have 0 divided by 5 root 5, and then 0 divided by 5 root 5 is equal to 0. Therefore we have the directional derivative of the function at the point 2, 1 to be equal to 0. So to question 3, we are going to find the directional derivative of this function at the point 1, 1, 2 in the direction of the vector v equals 2j minus k. Now in this example, we have a function of 3 variables. So the directional derivative of this function x, y, z is equal to the dot product of the gradient vector and the unit vector u cap. So we have the gradient of the function, or the gradient vector, to be equal to the vector which has components fx of x, y, z, comma fy of x, y, z, comma fz of x, y, z. So we are going to find fx, fy, and then fz. So for fx, that is the partial derivative of the function with respect to x. We are going to consider this function, and then we differentiate with respect to x. We keep y and then z constant. Now using the shortcut form of the chain rule, we are going to drop down the exponent, which is 3 over 2. We are going to differentiate with respect to x. So we differentiate x and then we have 1. And then we are going to repeat what we have inside here, which is x plus 2y plus 3z. And then we are going to reduce the exponent by 1. So 3 over 2 minus 1, that is equal to 1 over 2. So finally, we have fx to be equal to 3 over 2 times x plus 2y plus 3z, all exponent 1 over 2. Now you can treat this or represent, the expression in the bracket as the square root of the expression you have. But for now, let's just leave it like this. So this is fx. So fy. So using the same approach, we are going to drop down the exponent 3 over 2. We differentiate with respect to y, so we have 2. When you differentiate 2y with respect to y, you have 2. And then we are going to repeat the expression inside, and then we are going to reduce the exponent by 1. So that becomes 2 cancels out 2. We have 3 times x plus 2y plus 3z, all exponent 1 over 2. And then for fz, that is equal to, we have 3 over 2. We differentiate 3z with respect to z. We have 3, and then x plus 2y plus 3z, exponent 1 over 2, that is equal to, this becomes 9 over 2 times x plus 2y plus 3z, all exponent 1 over 2. Now notice that when we differentiate with respect to x, y and then z becomes constant. When we differentiate with respect to y, x and then z become constant. And then when we differentiate with respect to z, x and y become constant. So this is fx, fy, and then fz. So for the gradient function, or the function, or the gradient of the function f of x, y, z, that is given by the vector which has components 3 over 2 x plus 2y plus 3z, all exponent 1 over 2, comma 3 times x plus 2y plus 3z, all exponent 1 over 2, comma 9 over 2 times x plus 2y plus 3z, all exponents 1 on 2. So that is the gradient of the function. Now the next thing is we need to find the gradient of the function at the point 1, 1, 2. So next we find the gradient of the function at the point 1, 1, 2. So what we are going to do is we are going to substitute 1, 1, 2 in place of x, y, z. Now you realize that this expression repeats for each of the components. So let's just evaluate that. So let's say we have x plus 2y plus 3z, all exponent half. And then we can represent this as the square root of the expression we have. We have x to be 1. So 1 plus 2y, y is also 1. And then 3 times z, z is 2. So this becomes 1 plus 2 plus 6. And that is 9. So the square root of 9 is equal to 3. So we have 3 here. So therefore we can have this to be 3 over 2 times 3, comma 3 times 3, comma 9 over 2 times 3. And that becomes 9 over 2, 9 times 3, 27, so 27 over 2. So basically this is the gradient of the function at the point 1, 1, 2. The gradient of the function at the point 1, 1, 2. Next, we need to evaluate the unit vector from the direction vector. So let's do that here. So we are going to let the unit vector be u cap. Okay, we are going to let the unit vector be u cap. So let u cap be the unit vector. So that's the unit vector. And then we have the unit vector u cap to be equal to, now we have the direction vector to be 2j minus k, which means that we have no x component, or the x component is 0. So that becomes 0, 2, minus 1. Okay, 0, 2, minus 1. So the unit vector is equal to the direction vector divided by its magnitude. So we have the magnitude to be 0 square plus 2 square plus negative 1 square. So that is, we have 0, 2, negative 1, all divided by, now 0 square is 0, 2 square is 4, and then negative 1 square is 1, so that becomes 5. So we have the square root of 5. So the square root of 5, and that we have the unit vector to be equal to 0, 2 over root 5, negative 1 over root 5. So this is the unit vector. Now, to find the directional derivative of the function at the point 1, 1, 2, that is equal to the dot product of the gradient of the function at the point 1, 1, 2, which is the vector having components 9 over 2, 9, and then 27 over 2, dot the unit vector having components 0, 2 over root 5, negative 1 over root 5. So we are going to multiply corresponding components and then we add them up. So 9 over 2 times 0, that is 0, plus 9 times 2, which is 18. So we have 18 over root 5 plus, so this time we have negative 1 here, so that becomes minus, or you can, better still make it plus, and then into bracket, negative 27, so that you always remember that we add corresponding components. And then 2 times root 5, so this is 2 root 5. Now we want to find the LCM. The LCM becomes 2 root 5. So 2 root 5 divided by root 5, that is 2. 2 times 18 is 36. So we have 36, and then minus 2 root 5 divided by 2 root 5, you have 1. 1 times 27, so that is 27. Now 36 minus 27 is equal to 9. So we have 9 over 2 root 5. And this happens to be the directional derivative of the function at the point 1, 1, 2. So that's it for today's video. Thanks for watching, and see you in my next video. Bye bye.